Okay, welcome back. This is a presentation on Vector Operations 2, which is based on material in section 10.5 in our textbook. And I'm pretty much going to do most of these topics, but it's going to probably take two or three different parts. Okay, as far as computing work, I'm not sure if I'm going to do that. I may not get there. Well, let's move on. Okay. So we've already done an introduction to vectors, and what this section deals with is something called the vector dot product, aka also known as the inner product or the scalar product. And the definition is if vector v, and notice again I'm using boldface for vectors and boldface I and boldface j for the Kronecker vectors, which, just to remind you, are the unit vectors, this one in the horizontal or x direction and this one in the vertical or y direction. So you have two vectors, v and w, and the components are a1 and b1, a2 and b2. The dot product v dot w, and it's not simple multiplication, so a little bit more than that, is defined as follows. You multiply a1 times a2. So in other words, we're multiplying the coefficients or the components in the I direction, and we're adding the product of the components in the j or the y direction. Notice v dot w is a scalar. It's not a vector. So this is a numeric quantity. It doesn't have a direction. It simply has a magnitude. Okay, so moving along. So using the definition, let's compute the following. Okay, had to adjust that a bit. I knocked into it. Okay, so there are two approaches that we're going to take. First approach, well, I guess you can sort of do a few of these mentally, but the first one, v dot w, is 2 times 5, and then plus negative 3 times positive 3. So 2 times 5 is 10, and negative 3 times positive 3 is negative 9, and combining them, we get a total of 1. Okay, so this is how it works. Okay, so looking at A and B, you can see that the dot product appears to be commutative. The order does not matter. And computing a dot product with itself, well, you go 5 times 5 plus 3 times 3, and you get 34. Okay, so forth and so on. This is fairly easy to do. And again, the dot product is a scalar quantity. It's not a vector, it's just an amount. It does not have a direction. Let's look at E. Part E, let's go back a bit, is the magnitude or the length of vector v. And we've learned in past times that the magnitude is simply, we use the Pythagorean theorem on the components. Okay, so you have 2 squared plus negative 3 squared, radical 13. Similarly for w, you have 5 squared plus 3 squared, 25 and 9 is 34. Okay, so here we go, moving along. Finding dot products with vectors in component form. Now notice over here, we wrote vector v as 2i minus 3j. What we could have done is we could have used those angle brackets and said 2 comma negative 3. Well, that's what we're using here. So we have some different vectors, u, v, and w, and we're performing these computations. So I guess we can do the first one mentally. Okay, so 2 times 5 is 10. I'm doing u dot v. Negative 2 times a is negative 16. So 10 and negative 16 is negative 6. So here's our answer of negative 6. And you can work these out. Okay, so let's look at B. All right, in B, u dot v is negative 6. And again, notice this is a scalar quantity, and negative 6 times w, we're simply multiplying each of the components of w by -6, so 24 comma -18. This is a vector quantity. When you multiply a scalar times a vector, you get another vector. Okay? However, this is a dot product, so this is going to result in a scalar quantity. All right, so you can work through these. They're kind of obvious. Okay, properties of the dot product. There is a special handout PDF form on Blackboard with many properties listed. You can use that as reference. I'm just listing the ones here for the dot product. So here we go. U, V, and W are vectors. C is a scalar, in other words, just a number. We have already seen that the commutative property holds, the distributive property holds as well. And I can see what I should have done. Let's see, I should have had, no, this is perfectly acceptable. Okay, so it's U dot V plus U dot W, so it's a form of the distributive property. As far as scalar multiplication goes, you can apply the scalar to either of the vectors and then do that dot product. Okay, V dot V is the square of the magnitude. Notice this is a scalar because V dot V, by definition, dot product is a scalar. Okay, over here, notice the two different zeros. This is the zero vector, namely angle brackets 0, 0 dot. So this must be a scalar. So this is a scalar, this is a vector. Okay, alternate way to compute the dot product. Now, so far, let's go back to the definition, way back in the beginning. Here was the definition of the dot product. It turns out the dot product has a very interesting interpretation. And we get it from the law of cosines. The dot product U dot V is the magnitude of U times the magnitude of V times the cosine of the angle between them. So what that lets us do is we can solve for cosine theta, and this gives us a way of determining the angle between two vectors. All right, so this is going to be extremely useful. Now, you're probably thinking, where did this come from? Let me show you. It comes from the law of cosines, and again, I got the philosophy that if you understand where something comes from, it gives you a better understanding of it. Okay, so here we go. Vector U and vector V meet at an angle theta. So they have a common beginning. And V minus U would be the head minus the tail. So in the arrow going from here to here, this is the head, this is the tail. The head comes from the V, and the tail comes from the U. That's why this is V minus U and not U minus V. So don't forget, vectors are always represented by head minus tail. Okay, by the law of cosines then, this quantity squared equals U squared, or I should say the magnitude of U squared plus the magnitude of V squared minus 2 magnitude of U, magnitude of V, times cosine theta. So this is the law of cosines. And what we're going to do is we're going to work this out. And magnitude of V minus U, the quantity squared, is going to be, well, what do you get when you square something? You dot product times itself, right? And you work this out using the distributive law we've had in the past. And look at what you get. You get, this is magnitude of V squared, this is magnitude of U squared minus 2U dot V. Now all of this is simply V minus U, the magnitude squared. So what I'm going to do on the next slide is this is going to replace this. Look at what we get. Okay, here is the magnitude squared of V minus U, which we just worked out. Here's the right side of the equation, and notice a lot of stuff cancels. The V squareds and the U squareds match up, so they go. And we end up with this, and we divide both sides by -2, solve for cosine theta, and there we go. So we have our alternate form of the dot product, all right? I can say that u dot v is, magnitude of u, magnitude of v times cosine theta, or I can solve for cosine theta, either way. So let us do an example. All right, example that we want to do is we want to find the angle theta between two vectors. So let's take a look at it. And the vectors we have are vector u is 4i minus 3j. And if you want to draw that in or sketch that in as a position vector, that's probably a good thing to do. And vector v, 2i plus 5j. You can do the same thing. And take a few moments and see if you can do the computation. Now, just going back here, look at the formula. You have u dot v, which you can do easily, right? And magnitude of u, magnitude of v, you work this out, you're going to get a numeric value for cosine, you're going to do an arc cosine and get the angle. That's the plan. So pause the video, see if you can go through with the numbers. Hold on. Okay, I'll assume that you're back. Let's look at the next slide. We're going to go through it step by step. We're going to compute u. We're going to compute u dot v, magnitude of u, magnitude of v. Here we go. U dot v is -7. And how do we get that? Well, let's just go back here. 4 times 2 is 8. -3 times 5 is -15. Add those guys up and we get -7. Okay, the magnitude of u, well, again, go back and look at what u is. U is 4i minus 3j. So the magnitude of u would be 4 squared plus -3 squared under radical, and the magnitude of v would be 2 squared plus 5 squared under radical. And you can see we work these out and get 5 and radical 29. Now all we do is we put them into the formula. Okay. Cosine theta, u dot v over magnitude of u, magnitude of v. You put the numbers in, you get this crazy thing which you can only do on your calculator. So we approximate it by -0.26, and you use your calculator. So our cosine of that value, and you got to be in degrees now, would be 105 degrees. Okay, at this point, I'm all about making diagrams. I'd rather look at a picture. So I'm going to, here's the picture or the illustration. And here we go. U was 4i minus 3j. So we're going to make it a position vector starting at the origin. 4 down 3. So this will be 4i minus 3j. And v, we're going to make that a position vector as well. And, even if they weren't, they could have been extended and see the angle that the extensions meet. So this is not a real problem. So vector v was 2i plus 5j. So 2 up 5. And clearly the angle looks obtuse. And in fact, it is 105 degrees. And that's what we figured out. Kind of interesting. Okay, determining whether two vectors are parallel. Okay, two vectors u and v are parallel if one vector is a scalar multiple of the other. In other words, if u is some multiple of v for some scalar, non-zero scalar c. Geometric, so this is the definition. Geometric consequence. If two vectors are parallel, the angle between them is 0. Now, think about what you know about cosine and imagine in your mind the graph of the cosine curve. Okay, the cosine curve at 0 has a value of 1. So in mathematical terms, all we need to do is use this formula, which, don't forget, is just another version of the definition of the dot product. Use this formula, and if you get a 1, it means that the inverse cosine would mean that the angle would be a 0 degrees. Okay, so that's how we tell. So let's look at an example. Demonstrating two vectors are parallel. Show the vectors u and v are parallel. Well, again, you go through the routine. U dot v, 3 times 6 is 18. Negative 1 times negative 2 is 2. 18 and 2 is 20. So the value of u dot v is scalar value of 20. And now let's do magnitude of u times magnitude of v. Well, 3 squared and negative 1 squared is 9 and 1 is 10. That's a radical 10. And 6 squared and negative 2 squared is 36 and 4 is radical 40. Multiplied out is 400. Square root of 400 is 20. 20 over 20 is 1. Okay, so we got the cosine theta is 1, and that occurs when the angle is 0. And I should have had 0 degrees here, but I'll fix that up in the future. Okay, so also notice that if I multiply this vector u by the scalar 2, 2 times 3 is 6, 2 times negative 1 is negative 2, so that goes back to our principle, right here, that one would be a scalar multiple of the other. Okay, so second interesting application is we can demonstrate that two vectors are orthogonal. Now the word orthogonal in plain English means meets at a right angle. So this is a word we use if we're talking about vectors. If we're talking about lines, we usually use the word perpendicular. So it means the same thing. It's just orthogonal is the word that we use with regard to vectors. All right, so two vectors are orthogonal if and only if the dot product is 0. Okay, so let's think about why that should be. So this would be a kind of diagram, and let's see. First of all, if the dot product is a 0, it means the cosine is 0. And again, think of the cosine curve. The cosine curve has a y value of 0 at pi over 2, 190. Well, that's orthogonal. It means meeting at a right angle. Okay, so let's do an example. Determining whether two vectors are orthogonal. Verify that the vectors 2i minus j and 3i plus 6j are orthogonal. Well, let's get an idea what these look like first. 2i minus j, we're going to treat these as position vectors. We start at we start here, move over 2 and down 1, right? Because the coefficient j is negative 1. So this would be vector v. And vector j, again, we think of it as a position vector. We start here at the origin, you go 3 over, 6 up, and that seems to be our vector w. If you take a look at this, they certainly look like they're perpendicular. What we're going to do now is demonstrate it. So the rule is we do the dot product, and 2 times 3 is 6, and negative 1 times 6 is negative 6. It is indeed 0. And again, the cosine of 90 degrees is 0. So that tells us that, the vectors are in fact orthogonal. Okay, next topic, orthogonal projections. I'll talk about this a little bit, but we're going to pick it up in the next part of this video for the simple reason that this is a difficult topic. So you got this new word, a projection. So let's talk about it a little bit. And think of a flashlight. Okay, I've got a little icon of a flashlight here. And think of a shadow. When you have a light source, let's say a flashlight, and you shine it at an object, that object will cast a shadow on a wall or a background. And that's called a projection. So that's all that this is about. So let's take a look at this. And given two non-zero vectors v and w, okay, there they are. Here's a situation where theta is acute, and here's a situation where theta is obtuse, okay? So a third vector called the vector projection of v onto w is shown in each figure and is denoted as this. So it's projection v on top of or onto w. So if you take a look at this diagram here, here's your flashlight, and what happens is a shadow is forming on this line, and this line is the line which vector W lies on. So vector W is not the entire line or not the entire array. Vector W simply lies on this line. And a projection, right, you have a perpendicular here. The actual shadow is this length, which is outlined in blue. So this is called a projection of V onto W. Okay, so the projection is not the entire vector W. Doesn't need to be. Okay, now looking at this type of situation, you can see the same type of thing is happening. We're shining a light source onto V and perpendicularly onto this line in which the vector W lies, and this length here, from here to here, is the projection of V onto the line of W. Notice that it's not actually on any part of W in this case. It is, and that's possible. It just happens to be that since theta is obtuse in this situation, that the actual shadow or the projection is this length here. Okay, so it's on a line that W lies on, but we're going to call it the projection of V onto W. So when you see that word projection, you just think of shadow. Now what's going to happen is we're going to pick this up next time. Okay, so I'm going to stop here and we'll pick this up next time.